Yeah, so please type in the chat box, students. Am I audible to all of you? Yeah, audible? Good morning all of you guys. Yeah, good morning. So please type in the chat box. Am I audible to all of you? Audible, right? Great. Okay. So first of all, I welcome you all to this fast track course of mechanical engineering, and the subject that we are going to start is fluid mechanics and fluid machinery actually. Okay. So till yesterday, Shivam sir has taken you thermodynamics, and also Vijit sir has taken you theory of machines actually. So आज से मैं fluid mechanics लेता हूँ, and also in the evening sessions, Ramanand Bansal sir will start strength of materials in from today's class. Okay. So I hope you'll actually continue the learning of this new subject. And in this particular course, first of all, I'll give you the basic idea on what are the topics we are going to cover. So हम इस basically इस syllabus में mechanical के साथ पूरा XC का syllabus भी cover कर सकता हूँ, and also जब हमने questions solve करते हैं, so mechanical के साथ XC का models और XC level का questions भी हम solve करेंगे इस sessions पे, ठीक है? And coming to this first particular lecture, today's lecture will be on this fluid and its properties, जो पहला chapter होता है. So सबसे important chapter है, क्योंकि सारे properties का idea इसी chapter में हम पढ़ाते हैं. Okay, so that's why this is one of the most important chapters actually, fluid and its properties. And also हर साल गेट एग्जामिनेशन में इस चैप्टर से बिल्कुल एक क्वेश्चन भी आते हैं. ओके, सो लेट्स गो फॉरवर्ड. इन दिस पर्टिकुलर lecture that we are going to cover, we are going to see definition of fluid very basically. As you know, this is again a fast track course, and we will look at the following properties of fluids like density, viscosity, dynamic, and of course we will also see kinematic viscosity and bulk modulus. And surface tension, I have changed the color because surface tension is actually a binary property. Okay, so survey notes, okay, you can make notes also, but anyway you'll have also the PDF available, okay, in the apps. You can have the links in the below in the description, so you can have the links as well. Okay, and we will also study about rheology, non-Newtonian fluids, and in the last we will solve about numerical questions. Okay, so we'll see the consequences of this surface tension, capillarity, all these things we will see, but we'll see very in a fast go. Okay, so are you all ready to start the sessions? So please type in the chat box. Are you all ready for this? Shall we start? Okay, fine. So all of you show your energy ones. We'll solve. Okay, now let us see basically in the definition of fluid. So fluid is any substance which deforms continuously under action of even infinitesimally small shear stress. Correct? So what happens normally if you take any fluid? Let us suppose you have a fluid, for example. Now अगर किसी लेयर पे हमने एक थोड़ा सा shear stress apply किया तो, so layers will keep on continuously deforming, right? So like for example, let us suppose if you take one set of molecules here, for example, okay, so let us suppose these are different molecules, for example, of different layers. Then what happens with respect to time, if you apply any small shear stress like this, then with respect to time these molecules will actually start moving. Okay, like for example, let us suppose here you have a flat plate. Okay, now here if you have a flat plate, then definitely this flat plate at this particular point, the relative velocity between the fluid and the plate is actually 0, and this condition is called no slip condition. क्योंकि fluid के पास एक property होता है which is called viscosity, and this viscosity is actually called the stickiness. Okay, so because of this viscous property, the layer which is actually in contact with this particular plate will have the same velocity of the plate. Okay, so this is called relative velocity condition, and this is also called the no slip condition. If plate is moving with 5 meters per second, this fluid layer will also move with 5 meters per second. Clear? So that's how there won't be any velocity variation between the layer in contact and also the plate definitely here. Okay, so that's why this U relative is actually 0 at the interface, or generally at any solid fluid interface. Okay, so is this clear to all of you? Please type in the chat box. I'm going in a very quick way, so please type in the chat box. Is this clear? Did you all understand about the no slip condition? No slip condition? Yes or no? Right? Come on, fast. Okay, now if this is no slip condition, now if you see basically the main difference between a solid and a fluid, in case of solids, let us suppose if this is a solid, for example, you have locked this solid, for example, okay, and if this is solid, okay? And let us suppose you have fixed this. Now in case of solid, if you apply some shear stress, then what happens? Definitely, depending upon the elastic properties of the solid will actually deflect, correct? Like for example, the solid which is initially in this condition, now will take maybe this condition, correct? And this deflection is gamma, which is the shear strain rate, obviously, okay? So this is gamma, and as per this Hooke's law, we know tau is actually proportional to gamma, obviously. Shear stress is proportional to shear strain, and we connect them by shear modulus G, okay? But in case of liquids or in case of fluids in general, the situation is slightly different. Whenever you apply the shear stress tau, what happens is these particles, look, definitely this particle is having zero velocity. Now let us suppose you are applying shear by moving a plate, for example, okay? Let us suppose you have a plate here and you are trying to pull this plate at some velocity u, and that's how actually you are applying shear on the fluid. Then what happens? This velocity is zero, and this velocity, because of the same condition, this velocity will be same as this plate velocity. That means if I define a coordinate system, look, if I have this is x coordinate and this is y coordinate, you can understand one thing: as y increases, this velocity of the fluid layers also increases, correct? If I take, for example, u is the velocity of any fluid particle, I'm taking a one-dimensional simple case to make you understand. Now if these particles are actually moving, then definitely you can understand one thing: because of this fluid moving at high velocity, definitely this particle which is here will move at a higher velocity as compared to this particle, yes or no? And as you go in the upper direction, the velocity of the layers keep increasing because the distance from the plate is actually away, right? Because you can see the presence of the, because you can understand one thing, this fluid layer is in direct contact with the plate. So the fluid layer at the plate know that there is a plate here, but even though these layers are not in direct contact with this plate, still the velocity gets slowed down because there is actually some message that's going to these layers of fluid that there is a plate here, so you guys please slow down. Now who is the messenger that's traveling? Can anyone tell me? Can anyone tell me what is the messenger, or what is the thing that's telling these fluid layers to slow down? Can anyone tell me what is the property or what is the messenger that's actually telling these layers to slow down because of the plate here? It is intermolecular forces, and normally in case of liquids that is due to the viscosity, obviously, okay? Viscosity. Now if you see in this case, coming to one important understanding, this is at time t is equal to 0. If these are the positions of the particles, then at some time t is equal to say 2 seconds, for example, definitely one thing is very clear: this particle moves little far, this particle moves slightly less as compared to this, and like this you can have actually, okay? So you will actually have certain velocity profile which actually changes with respect to y. Means as y changes, this u will also change actually here, okay? And now one important thing here I want to tell you, later in when I'm teaching Navier-Stokes equation at the later stage, you will come to know, having this u of y doesn't always mean that there is a maximum velocity here and there is a 0 here, okay? It can be 0 here because of the plate. Means my question is, if you have a plate moving at u, for example, if you see, if this is 0, for example, and if this is u, it's not guaranteed that all the layers here, all the layers here will have a velocity less than u. Sometimes it can happen that the velocity at some location can be more than this u actually, okay? So here the velocity can be u is actually greater than u infinity. This can also happen, okay? And how and when it happens, I'll actually tell you later when we talk about the Navier-Stokes equation and the 𝐂𝐸𝐻 flow, okay? But right now there could be a possibility that here, if this is moving at u infinity, some layer between the plate and the top surface can move at a velocity which is higher than u infinity actually, okay? So this is one very important interview question also. Many times they ask you that if this plate is fixed and if this plate is moving at u infinity, can any layer in between can have a velocity which is more than u infinity? And generally people say no, because they feel that here the velocity is actually maximum, but it need not be the case, okay? I'll show you how and this happening when it is Navier-Stokes equation, okay? Now this is greater than u infinity. Now the main story here is, if you take any thickness of fluid dy, for example here, definitely on every layer there exists a shear velocity, correct? So there is also shear stress as a function of y, correct? It also changes obviously along this direction. Now if you want to relate shear stress and shear strain in case of solids, this deformation is actually finite, yes or no? Like for example, if I take some small elastic material and if I apply shear stress, for a given amount of shear stress, the vertical faces will actually get deflected by some finite amount. But in case of fluids, this deformation means basically, let us suppose if these particles are moving like this, these particles will not stop here, correct? With respect to time, they keep on flowing, okay? So that's why at time t is equal to 4 seconds, maybe this could be the graph. So this could be the position of this particles. So basically, with respect to time, these things keep on increasing, okay? The velocity keeps on increasing. So therefore, in fluids, shear stress is actually proportional to shear strain rate actually, okay? And let us suppose if this is xy, then the rotation is in the xy plane about this axis is z. So we write this as shear strain in the shear strain rate in the xy plane, okay? Because if you see, let us suppose if you take a fluid block for example, let us suppose if this fluid block is deforming in this direction with respect to time, okay? So like this, then this rotation of the faces is about this axis and this rotation is happening in the xy plane. So we denote it with gamma of xy, where gamma is this at any given instant, okay? So this is gamma xy, and this can be written as tau is proportional to d by dt of gamma of xy actually here, okay? Now if someone asks you about this, this is actually called Newton's law of viscosity. Newton's law of viscosity, okay? So this is Newton's law of viscosity, and here you can understand one thing, this shear strain rate need not be always equal to du by dy, okay? Look, I'm telling you, tau is actually proportional to gamma dot xy, and in many books you also see tau is proportional to du by dy, okay? This is the actual Newton's law of viscosity and it is always valid, but this is only a special case. Okay? Later when I'm teaching you fluid kinematics, you will see gamma dot xy, shear strain rate in the xy plane, is actually dou u by dou y plus dou v by dou x actually here, okay? So this is the actual expression for the shear strain rate. How this is coming, I'll show you in fluid kinematics, maybe in the next 2 chapters we'll see. But this equation, if you apply certain special cases, like let us suppose if the fluid is actually moving only in this direction, only in this particular direction, only one dimensional velocity, only one dimensional, and also let us suppose if this is x and if this is y, obviously you have only velocity is equal to u I, that's it, and this u, if it's only a function of x, only a function of y actually, then only this expression is valid, okay? Like I'll explain you with a simple example. If you see, for example, in this case, if you take a small element of fluid, okay? If you take a small element of fluid, for example, let us suppose if the element is initially like this, okay? Now, because of shear, let us suppose this element got deflected like this, for example, okay? And in a time t, let us suppose in time t, in a time small time dt, let us say in a small time dt, this particle went from this location to this location, and this particle went from here to here actually, okay? And if this is gamma, this also gamma we are taking right now. Now if you see this value d gamma by dt, actually I'll show you how this d gamma by dt is actually equal to du by dy in this case, okay? Sir please say a bit slow. ठीक है, लेकिन स्लाइड पे एक फास्ट ट्रैक, एक बुलेट ट्रेन का इमेज है ना, देखा सभी? I'll show you. हाँ, you see here, what is this train? Sir, my fluid was remaining, so can I follow this course? Yeah, definitely guys. Just a minute, a pop-up came actually. Yeah, no thanks, fine. Oh, just a minute. Okay, yeah. So, can anyone tell me that this d gamma by dt can be equated to du by dy here, okay? So, let us see. Okay, I'll go a bit slow, okay? I'll go a bit slowly, no issue. Now, if this is d gamma by dt, you can understand. Let us suppose if this is the particle, let us suppose if this is dy, because we are taking a small fluid element here to understand the things. If this height is dy, now let us suppose here if the velocity is u, for example, then can anyone tell me in a small time dt, what is the distance traveled? If this layer is moving with velocity u, for example, then can anyone tell me what is this length actually? This is nothing but the distance traveled by this particle in a time dt, and we know that this particle is moving with a velocity u. So can anyone tell me what is this length? So in fluid there is shear force present, or we should only consider velocity? Shear strain is what you have to take. Okay, can anyone tell me what is the distance of this? These particles are moving with a velocity u and in a time dt, obviously. Okay, so this is actually u into dt, because you know distance is equal to velocity into time, correct? You know this is u into dt, because I simply here this particle is moving with u velocity, so in a time dt this particle will travel u into dt distance, correct? Velocity into time, correct? So therefore if you apply this expression d by dt of, now let us see, gamma is nothing but, because this gamma is nothing but, so this gamma for a small time interval, if you take tan gamma is equal to gamma, then what you get actually, so tan gamma is equal to gamma, so tan gamma is from this triangle u dt divided by dy. Okay, so u dt divided by dy is what you have. Okay, so you have u dt divided by dy obviously here. Okay, now if you see for example this dt, if you take very small value and if u is only a function of v, what happens, this dt gets cancelled and you have du by dy actually here. Okay, here you may see that it is differential, but actually a small distance traveled in a small time will actually give you this. Okay, so du by dy in this case. समझ नहीं, एक बार फिर से repeat कर दीजिए please. Yes, I am repeating. Normally whenever you have a fluid layers which are flowing like this at any particular location, definitely the fluid is subjected to some shear stress. That's why the fluid is moving. Okay, so whenever there is a velocity changing in the y direction, definitely you also have a shear field which is actually changing, and because of this shear only these layers are moving actually. Okay, if there is no shear stress acting on the layers, then definitely fluid will not move. It's called the static condition. Okay, which we will see in tomorrow's class, fluid statics. But right now you can understand one thing: if this is there is velocity field which is changing with y, then definitely there is also a shear field, means at a particular location of y there is definitely some particular shear stress acting, and because of this shear stress these layers are actually moving with some velocity. Okay, so if someone asks you about Newton's law of viscosity, clearly you can say this is the Newton's law of viscosity, and actual expression for the shear strain rate is this. And in this particular case, whenever you have a 1D and all the layers are moving straight and u is depending only on y, what is the meaning of u depending only on y? What is the meaning of this? Look, I'll tell you. Let us suppose if fluid is moving, then at any distance y, if you take the particle velocity at this location and also at this location, there is no variation. Okay, so if you take this as the x direction and this as the y direction, then between these 2 points at same level of y there is no velocity variation actually here. Sir, thoda slowly padhaiye, fast hai bahut samjhe. Acha fine, I'll teach you slowly. Okay, so see here, if this is y, what is the meaning of this statement is actually there is no velocity variation between these 2 locations, because at these 2 locations even though x is different, y value is same. Okay, so if y is same between these 2 points, because this is a horizontal line and in this point on this line at these 2 points the y value is same, so whenever y value is same this function will not change because this y is changed. Like for example, let us say this is you know, ay plus by square, something like this. Okay, some equation for same value of y this expression will be same, correct? So u did not change between these 2 points. But if you take 2 points like 1 and 2 somewhere here, these 2 points are having some change in y, so definitely the velocity is different at these 2 points. Understood? Did you all understand? Did you all understand this clearly? Did you all understand what the meaning of u depends only on y? Clear? This is valid for all layers. Yes, these expressions are valid for every layer of fluid. Okay, u depends only on y means velocity of the layers changes only with respect to y. Okay, it doesn't change with respect to x. Clear? That's what we mean. And obviously when this function depends only on y and v is 0, for example, let us suppose if v is 0, what is v? Vertical component of velocity, correct? You know this, ui plus vj. So this is x component of velocity and this is y component of velocity, and all these particles are moving only in the x direction, so there is no y component of velocity for this. And if this is depending only on y, then this partial derivative can be written as exact derivative, and that's how this changes to this actually. Okay, clear? Okay, Anchal, I'll move little slowly. Okay, fine. Is this clear? Now let us see if this is the case. We have this d gamma by dt, shear strain weight, or sometimes you write this as tau is proportional to gamma dot xy. Okay. Now generally in case of very small velocity profiles or in thin gaps like clearance between shafts or movement of fluid in very thin channels, in these kind of situations, what you have is, look, I'll ask you one thing, so please say. It is purely an assumption, okay? Again, it is purely an assumption. Let us suppose this gap is very, very small. Then, let us suppose if a fluid particle is here, effectively the fluid particle only can have motion in this direction, yes or no? Because if the particle try to move in this direction, for example, within very less distance, it will again hit with the walls and it should come back. There is no provision for the fluid to go in this direction, okay? So effectively in this thin gaps, the fluid can move only in one direction effectively, because this particle, if it has any y component of velocity, the fluid motion or the fluid movement cannot sustain for a long time, because there is physically some solid boundary present here, okay? So that's why what happens, you can see this depends only on y in majority of the thin gaps and all, okay? Now if this is very thin gaps, then definitely, as I told you, this gets converted to du by dy. That's why in your first chapter, fluid and its properties, all the times we write this expression very repeatedly, okay? Because of this particular understanding. Because in first chapter, in fluid and its properties, whenever we are dealing, we always deal with thin gaps, small clearances and all. So that's why whenever we have this, we generally go with this du by dy, obviously. Clear? Because in first chapter, majority you never see I'm using this expression. You always see me using this. The reason is here. Got it? Good morning, Anjit. So please type in the chat box. Is this clear to all of you? This is also valid for ideal fluid. Yes, in case of ideal fluid, definitely this shear strain weight will actually be valid, but shear stress will be actually 0 because of one proportionality constant actually, okay? Now tell me one thing, we know that tau is actually proportional to d gamma by dt. This is here. Now since there is a proportionality symbol, to make it an equation, what we have to do, we should actually keep a proportionality constant, yes or no? And so let us see if this is tau is equal to k into d gamma by dt, okay? This is what we have, d gamma by dt. Or to make the explanation clear in small scale, let us suppose if I take tau is equal to some constant k into du by dy actually here, okay? This is what you have. Now I want to ask you one thing, k into dy by du, dy by du by dy, right? Or d gamma by dt. Yeah, we can have d gamma by dt. Now sorry, there is a question. So can a fluid deform indefinitely under the action of smallest force? Yes, if the force is shear, definitely the fluid can keep deforming, okay? Now let us see, I want you to have some understanding on this constant. What is that constant? Tau is equal to k into du by dy. For example, if you take this, k is actually shear stress for creating velocity gradient, yes or no? This is what you have. So that's what we have k from this equation. So Parakram 2025 बैच में FM आप लोगे क्या? हिंदी बैचेस को शिवम सर लेते हैं, इंग्लिश बैचेस को मैं लेता हूँ, okay? So see here, if you have this flat plate here, for example, now I want you to understand something. See, this is y and this is x, for example here, okay? Now let us suppose if I take this block of fluid, for example, this is some small dy. This quantity tells about one thing, that to move these layers, what should be the shear stress I should apply. That's what this constant k tells you, yes or no? This constant k tells you that to provide 1 unit of this velocity gradient, what should be the tau I should apply, yes or no? Now try to understand one thing. Let us suppose if this is the layer, if this is moving with u and if this is moving with u plus du, for example, So obviously the velocity gradient means within a gap of dy, the change in velocity is du. So definitely velocity gradient is du by dy. Now try to tell me one thing. If this gap has to be, let us suppose if I want to maintain this du by dy, for maintaining this du by dy, if tau is high, that means, what is the meaning? To move this layer with respect to this layer, I have to apply high amount of shear stress. That's what this is telling me. Yes or no? Can anyone tell me this? Can anyone tell me that if I want to create this, if I want to apply tau is high, that means I have to apply, I feel very difficult to move the layers with respect to this. Yes or no? That means if I have to apply very high amount of force on the layers, that means the cohesion between the molecules in this liquid is very, very large. Can I say this? Can I say that if tau is high, that means cohesion is high actually, because these molecules are not allowing this layer to move easily, correct? Which means one thing, this constant K talks about the bonding between the molecules and how effectively the layers of this allow this layer to move, correct? So this property, or basically this is actually a measure of stickiness of the layers, or in case of liquids it is also a measure of cohesion between the molecules actually. Okay, so this constant K is actually measure of stickiness, and that's actually called dynamic viscosity. Dynamic viscosity. And you can see dynamic viscosity, this name as it tells you, it is dynamic viscosity, because you can feel this property only and only when the fluid is moving. Okay, let us suppose if the fluid is static and let us suppose you are not moving any layers, then obviously they won't try to pull each other. Yes or no? Because all the layers are at same velocity. But now when you try to move these layers, then this constant K, this shear stress tau comes into picture, and then only you can see, means whenever the fluid is in dynamic condition, only in that particular case you can feel this property, and this is called dynamic viscosity actually here. Clear? So that's why this is called dynamic viscosity, and generally it is denoted with the symbol mu. So that's how we have K is, basically mu is equal to tau by d gamma by dt shear strain rate, or it is also equal to tau by, this is not 2, okay, this is tau du by dy actually here. Clear? This is for all cases. This is only in 1D flow where u is only a function of y actually here. Okay, is this concept clear to all of you? Did you all understand the importance of this dynamic viscosity and how this dynamic viscosity is powerful, and what is the physical meaning of dynamic viscosity? Because if fluid layers are in static condition, you cannot see this, because obviously if fluid is in static condition, it cannot hold any shear stress. Okay, clear? Got it? अरे यार एक बात कम से कम चैट बॉक्स में टाइप कर लो, नहीं तो मेरे को कैसे पता चलेगा कि आप लोगों को समझ में आ रहा है या नहीं. All clear? Good. Now let us talk about this story a bit of mu. Okay, now dynamic viscosity. Dynamic viscosity. Dynamic viscosity. So if you take mu, what are the units? SI units. Let us say for example SI units. Okay, now clearly this property is nothing but shear stress by velocity gradient. So shear stress has the units of Newton per meter square, pascals. Du by dy, this is nothing but du is difference in velocity. Okay, so please a bit slow, you are too fast. Yeah, I'll teach it slow. So is it valid for Newtonian or non-Newtonian fluid? No, we are talking about Newton's law of viscosity, so only for Newtonian fluids. Okay, right now we are talking only on Newtonian fluids. Okay, now du by dy, so this is change in velocity. change in velocity and velocity has same dimensions, yes or no? Because let us suppose if change in velocity is some 10 kilometers per second, then obviously it's like change velocity. So this has units of meters per second divided by dy. Dy is nothing but change in distance, so dy has units of meter. So if you put here, mu is tau by du by dy, so if you divide this, Newton per meter square by 1 by second, so this gives you Newton second per meter square as the units. Okay, so Newton second per meter square, or sometimes this Newton per meter square can also be written as pascals or pascal second. Okay, that's how you have this. Clear? Now let us see in case of MKS. Obviously this, if you convert to MKS, Newton second per meter square, Newton can be written as mass into acceleration into second by meter square. This m and this m, this s and this s cancels, so kg per meter second. Okay, and clearly you can see conversion factor 1 is equal to 1 here. Okay, so 1 Newton second per meter square is same as 1 kg per meter second. That's why in many problems, to confuse you, they will actually give you the viscosity value in kg per meter second. Okay, expecting you to use some conversion property, okay, but conversion factor. But if fluid dynamic viscosity is given in kg per meter second, you need not use any conversion factor, you can directly use the value. The reason is 1 Newton second per meter square is same as 1 kg per meter second because of this simple conversion. Okay, now coming to CGS units, let us convert this to CGS. 1 kg per meter second is equal to 1. Now convert to CGS. Kg 1000 grams per meter 100 centimeters second is 1 second, obviously. Okay, now if you convert this, 10 square will cancel this 10 times, so 10 times of gram per centimeter second, and this gram per centimeter second is actually the CGS quantity, or you can say 1 gram per centimeter second is equal to this 10. If it goes to the other side, it is 1 by 10 kg per meter second actually here, and this is also same as 1 by 10 Newton second per meter square, because this and this are same actually. Okay, so 1 gram per centimeter second, so this is basically the CGS unit, and this is named after this physicist, which is Poise actually. Okay, so the CGS unit of dynamic viscosity is called Poise, and you can clearly see 1 Poise is equal to 1 by 10, which is 10 power minus 1 Newton second per meter square actually, because of simple conversions. Okay, so therefore 1 Poise is equal to 10 power minus 1 Pascal second. Clear? So that's what you have. So this is how you have SI, MKS, and also CGS. Clear? Yeah, 1 Poise is equal to 10 power minus 1. 1 by 10 you can see clearly. So 1 by 10 is 0.1. So 0.1 Pascal second. Okay. Is this clear to all of you? Please type. And obviously if you check the dimensions of mu is equal to kg per meter second. So mass by length into time. So mass, length inverse, time inverse. That's it. Because of this directly. Okay. You can see clearly kg per meter second. So obviously meter second is in the denominator, so LT should have negative powers of 1, kg is in the numerator, so m should have a positive power. That's it. So these are the units of dynamic viscosity. Clear? Yes or no? Please type in the chat box. Is this clear to all of you? Did you all understand these conversion factors? Why this 10 power minus 1 is coming? Why this 0.1 basically is coming here? All these things. Okay. Fine. Now, let us see one very important property before we go to some other things, before we go to certain dimensions. Many times, kinematic viscosity, if you see, this is denoted with the symbol nu actually. Okay, so kinematic viscosity. So kinematic viscosity is clear, right? Yeah, it's all clear. So kinematic viscosity is actually equal to mu by rho actually. Okay, and this property is very powerful property. Okay, you know why this property is actually very important, and also many times you can see this is called momentum diffusivity. Momentum diffusivity, which is very much analogous to thermal diffusivity alpha. Alpha, which is K by rho C. P general. Okay, so alpha is equal to K by HCP. These two are very similar terms and very important. This is especially extremely important in fluid mechanics, and this is extremely important in heat transfer, obviously. Now the question is why this is very important. That's the question. Okay, if you see, it is not just a simple ratio. To look, this is just a ratio of two properties, but in physical sense, this is actually very important because this property is a flow resisting property, because obviously you understood, if then viscosity is high, then definitely what happens here, the layers feel more difficult to move, obviously. So that means this has very high capacity of stopping its own flow, correct? Let us suppose if a fluid is having high dynamic viscosity, that means this particular fluid is actually having very high tendency to stop the movement of its own layers. Okay, so it actually stops its own flow. But this property density is actually flow supporting property. Flow supporting property. Okay, now what about this flow supporting property? I'll ask you one question. Try to answer this. Let us suppose you have 1 kg of cotton ball, for example, cotton, okay, made of cotton, and 1 kg of steel ball, and let us suppose both are coming towards you at the same velocity. Okay, in which case you feel it difficult to stop? 1 kg of cotton ball and 1 kg of steel ball are coming towards you with same velocity. In which case you feel it difficult to stop them? Cotton or steel? Cotton or steel actually? Obviously steel ball, we all know this, right? So it is steel ball. Now why steel ball is very difficult? Because even though masses are same, because obviously we know density of steel is actually very high. Okay, so density is actually measure of inertia. Okay, and whenever this fluid is trying to move, density of the fluid, density is that property of the fluid which tries to keep the flow maintaining. Okay, so that's why out of these two properties, one is actually trying to stop the flow and one is actually trying to sustain the flow. Okay, so that's why this property is called diffusivity. Diffusion means actually propagation, okay. So this ratio decides how effectively the fluid can move in actual case. Got it? Okay, so here you can see when this is trying to stop and this is trying to propagate the flow, this ratio actually brings out how effectively a fluid can flow under a shear stress, and that's why kinematic viscosity is very much important. Clearly here also you can see thermal conductivity will actually is a measure of how effectively heat can actually flow through a substance, and the rho Cp is nothing but heat capacity, the heat holding capacity of a substance. Okay, so this is also a ratio of two contradicting properties. One property will actually try to propagate the heat to the substance, and this actually try to hold the heat. Okay, it tries to store the heat actually. Okay, so that's how this is also a ratio of two contradicting properties which actually decides the effectiveness of the heat transfer in any medium, and this actually tells you about the effective momentum transfer, means effective motion of the flow in a particular medium actually. Okay, and here one important thing I would like to tell you, later in our discussions we will see one dimensionless number nu actually. Okay, and clearly this nu is the property which decides the nature of the flow. Like I'll ask you one question, tell me, let us suppose I have a requirement from one location to another location, I have to transport some fluid. Okay, so let us suppose this is for example Delhi and this is for example say Mumbai. I have to transport some fluid. Let us suppose I have a pipeline. Now depending on the things, I can choose my diameter. Yes or no? D is my choice. I can choose my diameter. Whatever the pipe I want, I can keep. Now let us suppose if I have the requirement of Q, since Q is equal to V average into pi by 4 d square, discharge into a velocity, we'll see all this, how this is coming and all. Now if you decide D, for a given Q, this V average can be adjusted accordingly. Yes or no? Which means, can you feel in Reynolds number, these two can be altered depending upon the situation. Yes or no? Of course losses and all will change, you can do little mathematical analysis, but right now these two can be chosen at your interest depending upon the application. But can you change this? Can you change kinematic viscosity? Can you change kinematic viscosity? Can you change these two of any substance? Of course, under high temperatures and all, you can change slightly, but very less. Okay, you can change very less. So this actually decides the nature of the flow at this particular condition. Okay, at a given values of V average and D, it is kinematic viscosity which decides the nature of the flow. I'll tell you how. Let us suppose I'll ask you a simple question. You can again answer this. इतना जल्दी Reynolds number आ गया है, FM complete हो गया क्या sir? नहीं केस ना. Let's focus. Okay, so see here, I'll tell you. Let us suppose you are going on a bike, for example. Okay, at let us say some 30 kilometers per second or 20 kilometers per second. Let us say you are going very slowly. At 20 kilometers per second, you applied some brake to your vehicle. Then you will stop smoothly or you will stop roughly. Can anyone tell me? At 20 kilometers per hour, if you are moving your vehicle and if you apply brakes at 20 kilometers per hour, 20 is generally very slow speed, correct? So at this slow speed, if you apply brakes, you will stop smoothly or you will stop roughly. 20 kilometers per hour actually. Okay? You will generally, it depends on the road, of course, flat road, okay? Smooth road, let us say. Enough friction, so smooth road. Generally, we stop smoothly. Now let us suppose you are going at 120 kilometers per hour or 130 kilometers per hour and then you apply the brake. What happens? Let us suppose instead of now going at 20, you are moving at 120 kilometers per hour and then you apply the brake. Then what happens? Of course, I am talking about the flat road, okay? Smooth road. If I am going at 120 and if I apply brakes, then obviously what happens? My bike will actually go in a very zigzag way and I will stop, correct? A very rough braking, correct? Accident bhi hota hai, correct? Okay, so but generally it goes very rough. Okay, same thing depend on will of God. Okay, so see here, I'll tell you one thing. Let us suppose if you have a flat plate. Let us suppose if the fluid is coming, for example, like this at U infinity. This plate will actually act like a brake to this fluid motion. Yes or no? Because as soon as the fluid starts entering this region, it starts feeling the effect of this viscosity. Correct? Now, try to understand. When this fluid enters, these two properties will come into picture. Yes or no? So, mu and rho actually. And you know from definitions, later you will see, this is inertia force by viscous force actually. Okay. Now, whenever these are coming in, because of this plate, you will start experiencing the viscous effects. Now, let us suppose if this fluid has high inertia force, means in this situation, mu by rho, let us suppose if this rho is very high. If this fluid is actually having high inertia, what happens? Even though there is a fluid which is present, even though there is a plate which is present here, this fluid, despite of having this plate, it will try to effectively continue its motion. Yes or no? Correct? Even though this plate is trying to stop, means even though you apply brake, but this fluid has very high inertia, then still it tries to continue the motion. Okay, so there happens high imbalance between these two, and definitely like in case of your bike, whenever at high speed you apply brake, there is a turbulence. Similarly here, these layers of the fluid will experience high turbulence or high zigzag or basically high roughness in the flow. Is this clear? And what does that physically mean? If this density is high, that means this kinematic viscosity is low. If this inertia force is high, obviously density is high, means inertia force is high, this Reynolds number will be high. Okay, and in this expression, if you put nu as low, then Reynolds number is high. That's how physically or mathematically. Now it's fine. Is it fine now? Yeah, is it fine now? Please type in the chat box. Yeah, fine, right? I think there was some power fluctuation. Suddenly it happened. Sorry about this. Yeah, let's continue. So here, practically, if you see, these two properties actually decide, means basically this quantity which actually decides the nature of the movement of the fluid in this region where you have both inertia and viscous forces. Understood clearly? So you can see this nu, because of this, actually decides this number, and practically these two properties will actually decide the movement of the fluid in this regime. Is this clear to all of you? Understood? Did you all understand why this kinematic viscosity is very important and how it actually denotes momentum diffusivity? Means when something is trying to stop the flow, how effectively the flow can still propagate. That's what actually nu tells you. Clear? How many of you like this explanation? Is this clear to all of you? How many of you learned this explanation in a nice way? Because this property is very powerful. Okay, later when we go with flow through pipes, or basically when we are applying Navier-Stokes equations and all, you will clearly see that this is the term which is really important. Okay, we'll see that. Okay, now let us see if you talk about the dimensions again. Dimensions of kinematic viscosity. Okay, now in this case of kinematic viscosity, you can see SI is Newton second per meter square into kg per meter cube, because mu by rho obviously. So if you simplify this, you will have something like meter square per second. Okay, so this is SI. So obviously this is also in MKS, because there is nothing like newtons or here. So this is meter square per second. Now coming to CGS, 1 meter square per second is equal to 1 into meter square. If you convert to centimeter square, 1 meter is 10 square centimeters. So 10 square whole square centimeter square by second actually. Okay, so this is 10 power 4 centimeter square per second, 1 meter square per second, and clearly 1 centimeter square per second, this is the CGS unit, is equal to 10 power minus 4 meter square per second actually here. Okay, and this constant is actually the constant of conversion, and centimeter square per second is named after this fluid mechanics scientist, which is Stokes actually. Okay, and Stokes made a lot of contribution in deciding the kinematic viscosity, and this all power of kinematic viscosity was actually discussed by this Stokes actually. That's why even in the Navier-Stokes equation, Navier and Stokes are basically two people. So we have Stokes, which actually made major contribution. Okay, so this is Stokes. So 1 Stokes is equal to conversion is 10 power minus 4 meter square per second actually in this particular case. Okay, and also if you check the dimensions of kinematic viscosity, we have meter square per second. So L square T power minus 1 is the dimensions. Clear? Got it? Okay, just simple conversions. Now let us see effect of temperature on mu, dynamic viscosity actually. Okay, now let us see, normally if you say fluid, it can be of two types in general, liquids and also gases. Now whatever the understandings I have given you, cohesion and all these things, that's for liquids, because I have taken different layers of fluid and all. So this layers splitting and all you can do generally in case of liquids. So in case of liquids, mu is due to, you have seen, molecular cohesion obviously, molecular cohesion. Okay, so this is molecular cohesion. Clearly we have seen that normally whenever the fluid layers are trying to move, then definitely because of the strong cohesion between the adjacent layers, the fluid is actually getting stopped. Okay, now try to understand one thing here. This mu is due to molecular cohesion obviously. As temperature increases, let us suppose in a liquid, let us suppose if there are two molecules which are connected by some bond. Now let us suppose if I start supplying heat energy to this bond, what happens generally? This particle will try to start vibrating, and this particle also starts vibrating in a random way, and this bond gets weakened. Yes or no? Correct? Can you understand? Let us suppose if two molecules are connected by a bond, obviously, if I start supplying heat to the molecules, then molecules will try to start moving in a random way obviously, and so I guess in gas also have layers like liquid. Yes, we have liquid gases also have layers like liquid, but there the mechanism of dynamic viscosity is something different. We will see. Okay, now if you see, if these two molecules are vibrating vigorously, this bonds between them gets weakened. Yes or no? Can you understand this? Yes? So please type in the chat box. Can I say this? All of you, I expect some quick responses, okay, because time is a bit short again. That's why. Yes? Now, if with respect to temperature, if bonds are getting weakening, that means cohesion will actually increase or decrease. Cohesion between the molecules. Cohesion between molecules will actually increase or decrease. What happens to this? Please type in the chat box. This will decrease obviously. decrease. So obviously as temperature increases, mu of liquids will actually decrease. Okay, so this is one very important statement. With increased temperature, viscosity is increased because of cohesive decrease. If cohesiveness is decreasing in case of liquids, then definitely viscosity also decreases, correct? So this viscosity will actually decrease. Okay, now if you want to model certain law, actually generally this mu of liquids is given approximately by an exponential model. Okay, so this is b by t, this is roughly exponential because this is based on experimental fits. Okay, so roughly experimental in this case. In some books you also see this as e power minus bt, both are same. To put this minus on this minus, the meaning is as temperature increases, this dynamic viscosity of the liquids decreases. Okay, if this is positive value, you know this t should be in the denominator. If this is negative, you can multiply this, because as temperature increases, this negative of exponential will actually decrease. Here also the same thing happens. As temperature increases, this coefficient decreases and exponential value decreases. Okay, so don't get panic by seeing two different expressions. Both these expressions will actually tell you the same thing. Okay, as temperature increases, because of this negative sign, this can be written in multiplication, because as temperature increases, due to this minus sign, this exponential will decrease. Similarly here, as temperature increases, this b being a positive constant, this value will decrease, which actually decreases this exponential. So as t increases, this dynamic viscosity of the liquid decreases. Okay, so that's what you have. Clear? Both these expressions are actually same, because in some books you find different nomenclature, so don't worry. Okay, and if you apply this to certain conditions, mu by mu naught, okay, like for example at some t naught, you know what is mu naught, so at some other t you have to calculate what is mu. Like for example, some reference condition is there, so at t is equal to t, what is this mu? That's what you have. So then definitely it's given generally by the logarithmic terms, t naught by t plus c into t naught by t whole square and all. Basically this is the expansion of this term when you integrate it. Okay, so don't worry, these two are actually the modelings that we generally go for dynamic viscosity of fluids. And if someone asks you that how we can actually talk about the dynamic viscosity, you can say it's roughly exponential with respect to temperature. Clear? Is these things clear to all of you? Yes or no? Please type in the chat box. Is this clear to all of you? This is the idea of how mu decreases. This is how mu decreases. That's it. Okay, with respect to some law. And coming to this, kinematic, this effect of gases, effect of T on dynamic viscosity of gases. In gases, the story is slightly different. Normally you might have studied in your schooling that, okay, slow, fine. You might have studied in your schooling that generally substances are into three categories: solids, liquids and gases. In solids, atoms are very closely packed. In liquids, relatively loosely packed. In gases, completely loosely packed. Okay. Now, whenever gases contains loosely packed molecules, the cohesion will still exist, but not up to the mark. Yes or no? The cohesion forces, because obviously as molecules go apart, cohesion forces between them decreases. So in case of a gas, yeah, I'll repeat. Okay, so in case of gases, what happens? The molecular spacing is actually large, so the cohesion forces, even though they are present, but they are actually very negligible in order compared to some other forces. Okay, now here in case of gases, what happens is, look, this property mu is actually resistance, is measure of resistance to its own flow. Measure of resistance to its own flow. Okay, now if this is measure of resistance to its own flow, let us suppose if we take two molecules, for example. Okay, so some molecules, let us take, for example, this is a gas. Actually, this is some container where you have some gas. Now try to tell one thing. I'll ask you two situations. Tell me in which situation the resistance is actually large. Okay, let us suppose if we take this molecule, let us suppose if this molecule is trying to move in this direction. Actually means, let us suppose if this molecule is interested to move in this direction, let us suppose at some particular instant. Now let us suppose there are two things which are trying to stop this movement. One is due to force of attraction of this molecule. Second is because of collision with this molecule also will get stopped. So there are basically two reasons here to stop the movement of this molecule, or basically to resist the movement of this molecule, because one is the cohesion between these two. Let us say this is case 1. One is because of the impact with this molecule, then also this molecule will experience certain resistance. Can anyone tell me out of these situations 1 and 2 which is highly powerful or which is more effective in stopping this molecule? This is cohesion and this is due to molecular impact. Can anyone tell me out of these two which is highly effective in providing resistance to the movement of this molecule? First or second? All of you. It is second, right? So this is highly effective because in case of in case of gases, molecules are loosely packed, so that's why the cohesion between the molecules is drastically low compared to the case of liquids. Okay, so that's why whenever molecular impact, yes, it is basically molecular impact. So in case of gases, the resistance to the movement is majoritarily offered by molecular impacts, and you know, generally whenever two molecules impact, or two bodies, even in collisions in mechanics you might have studied, if two molecules impact, what happens? This molecule and this molecule will actually involve in momentum transfer, yes or no? Because after impacting, the velocities of both these will change, because like how, let us suppose if I bring two hot bodies in contact, the temperatures will change because of energy transfer, correct? Similarly, if I make two bodies to collide, their velocities will change because of momentum transfer between the bodies. So therefore, this mu gases is due to momentum transfer. Okay, so this is due to momentum transfer, and this is basically due to the molecular impacts. So this sometimes is also called molecular momentum transfer, which is same, molecular momentum transfer. So this is how basically it happens. Now tell me one thing, you all know one thing, that kinetic energy of gases is proportional to the absolute temperature, correct? Who told you this? Your 12th class physics. Yes or no? Kinetic energy of the gas molecules is equal to 3 by 2 mRT or 3 by 2 RT. You have studied these things. Do you all remember this equation? Studied? Yes or no? So kinetic energy of the molecules depends on temperature basically. Okay. Now try to tell one thing here. Mu is due to the momentum transfer. Now tell me one thing. If I start heating this, okay. So let us suppose if I start heating this, and let us suppose I am trying to raise the temperature, then definitely the velocity of these molecules will actually increase. Yes or no? So the velocity as temperature increases, velocity of molecules increases. Now, hi Nayanda, okay, so see here. Now let me ask you one question again. Let us suppose if these two molecules are moving, for example, they are colliding, because of which you have viscosity. Now let us suppose if these two molecules are moving at some small velocities, let us suppose some 10 meters per second, and in second case these molecules are moving very highly, randomly, okay, let us suppose some 100 meters per second if both these molecules are moving. In which case, during the collision, there is high momentum transfer or high restriction actually. Let us suppose if this is moving at 10 and this is also moving at 10, whenever they impact, obviously this, like you can see, let us suppose if both the vehicles are going at some very low velocity, let us say some 10 kilometers per hour, and if they start hitting each other, then the impact will be obviously less, okay. But let us suppose if both are moving at 100 and if they impact, then definitely the impact will be high. So similar is the situation here. The resistance to the flow depends upon the velocity of this molecule also, correct? Means when this molecule is moving, how much momentum is changed in this molecule also depends upon this velocity of the molecule, correct? So that's why at high velocity, obviously the impacts or basically the momentum transfer between the bodies will be very large. So if momentum transfer is, molecular momentum transfer is high, that means the viscosity of that gas, or basically the resistance that the molecules feel for their movement, is also very high actually at that point. So therefore, as velocity increases, dynamic viscosity of gases, means the resistance which they face to move, also increases. Okay, so therefore in gases, mu gases increases with increase in temperature. Okay, clear? Is this clear to all of you? Did you all understand why in case of liquids dynamic viscosity will decrease and why in case of gases dynamic viscosity will increase? Because the physics that governs the viscous mechanism is different in both. One is due to the molecular cohesions, one is due to the molecular impacts. Okay, did you all understand why this is happening? Is this clear to each and everyone? So please type in the chat box quickly. Just a minute, this pop up again came. Just a minute guys, this pop up was coming. Yeah, clear? Now let us see one more thing here. So this is how the temperature will actually decide the dynamic viscosity in case of the gases. Okay, now coming to one more thing, pressure. Obviously because of the pressure liquids have very less impact, and in case of gases the effect of pressure for a given container can also be converted in terms of temperature using gas models. Okay, like for example in case of ideal gases you have PV is equal to mRT, and this effect of pressure can again be talked in terms of temperature obviously, and also if it is not ideal gas you also have the equations like van der Waals and Bertholdt's equations. You have a lot of different stuff where the effect of pressure can also be converted in terms of effect of temperature in general. Okay, in liquids the effect of pressure is generally very small because practically liquids are being incompressible, but in case of gases pressure do have significant change that depends on something called compressibility factor Z. Okay, so that again moves to thermodynamics. You all know compressibility factor Z obviously. So Z decides because when you apply pressure, what or how a substance behaves, that depends upon how a gas behaves. That depends on this compressibility factor. So that's why we again should go to thermodynamics for knowing that. Okay, so that's why we generally in fluid mechanics we don't discuss the effects of pressure on viscosity. Clear? So please reply to my question. Sorry, your question went BRC exam. Yeah, you can use that for BRC, no issue. Okay, is this clear to all of you? Now let us see kinematic viscosity. So basically if you see the how dynamic viscosity changes in gases, mu by mu naught is actually given by T by T naught power n obviously. Okay, these are absolute temperatures. Okay, so T absolute by T naught absolute. Absolute means 273 you have to add. So this is power law. This n is generally 0.7 for air of course. Okay, and you also have one very highly experimental law which is called the Sutherland law, where you see this mu by mu naught is equal to T by T naught whole power 3 by 2 into T naught plus S by T plus S actually here. Okay, where this S is normally called the Sutherland constant. Sutherland constant, and this S is normally 110 Kelvin for air at STP conditions, standard temperature pressure conditions. Okay, so this is what we have. So this is the Sutherland's constants actually, and this is the most experimentally fitted law for calculating the dynamic viscosities. So here I would like to tell you one thing. You can see in this case mu gas is proportional to square root of T absolute obviously, correct? Because in this, if you take this T power 3 by 2 and if you take T common here, this S by T ratio is generally small. It's like 1 by 2, 0.2, 0.3 of that range. So that will not create much impact because of this power. And if you take this T naught, all the constants, because this is anyhow constant, this is a constant. This T if you take out, T cancels this T power 3 by 2 square root of 3 times, and 1 plus S by T, at that S by T if you write in terms of exponential 1 plus S by T whole power minus 1, and if you expand using binomial expansions you will see this 1 minus S by T will be very small in general. Okay, that is very close to 1. So that's why this mu gases, dynamic viscosity in case of gases, is almost proportional to square root of T absolute. Okay, that's what we have. Clear? So square root of T absolute. So therefore in case of ideal gases, if you talk about kinematic viscosity of gas, which is equal to mu gases by density of gas obviously. Now this is proportional to, you have seen mu gas is proportional to T power 1 by 2 divided by density of gases. We know P is equal to rho RT. So at a particular pressure, you can see rho is inversely proportional to 1 by temperature. So this is proportional to 1 by temperature, and this implies your kinematic viscosity of gases is proportional to T power 3 by 2 actually. Okay. So this is proportional to T power 3 by 2. Clear? So there is one PYQ I think on this. So kinematic viscosity of gases will actually depend on T power 3 by 2, but of course this is absolute and this depends on T power 1 by 2. Clear to all of you? Okay. Is this clear? So which book is best for fluid mechanics? Solving problems, Frank and White. Okay. So shall I move forward from this? Is this clear to all of you? How all these relations are coming out? Okay. If all these relations are clear, then we will move forward from this particular location. Okay. Fine. All of you. Everyone please type in the chat box. Are you all clear for past 1 hour what we are teaching? Okay. Now let us see one more thing. Okay, clear? Yeah, good. Now let us see one interesting thing actually here. So if you see, normally I would like to ask you one question which generally was asked in some of the interviews. Out of these two fluids, these are the tau versus du by dy of two fluids. Out of these two fluids, one is water and another is air. Okay, so one is water and another is air actually. Okay, now let us suppose if this is the condition, can you tell me out of these two which is water? 1 and 2. Out of this 1 and 2, which is water actually? Out of these two, which is water? These are two graphs for tau is equal to du by dy, obviously. So can anyone tell me out of these two, which is for water? Anyone? Yeah, obviously this is for water and this is for air. Why? Because you know dynamic viscosity of water is actually very large, as compared to dynamic viscosity of air actually here. Okay, how do you know? Because practically moving your hand in air is easy as compared to moving your hand in water, because water offers you high resistance. Okay, so clearly you can see this mu of water is large as compared to mu of air. Now one more question is, let us suppose if this angle is theta. Okay, if that angle is theta, let us suppose if this is the graph at 25 degrees Celsius. Now let us suppose if I construct the same graph at 30 degrees Celsius. Can anyone tell me what happens to theta? Theta will increase or decrease or will remain same? Let us suppose this is the graph I have constructed at 25 degrees Celsius. Now let us suppose I have constructed the same graph at 30 degrees Celsius. Then can anyone tell me what happens to this theta in that case? Theta will increase or decrease or remain same? Come on, think. This is how you have to think. Okay, in GATE examination it's not like all the questions will come straight away from the notebook. Okay, but definitely every question will have its concept in our notebook, that 100% sure. But actually if you see in GATE examination, when you see a question, by reading that, using the knowledge in the books that or the concepts that we taught you, you should be able to think, okay, and then write the answers. Clear? Yeah, basically as in this case theta decreases. The reason for this is, you know, when you construct the same graph at t is equal to 30 degrees Celsius, let us see what happens. Since this is water, the dynamic viscosity of liquids will decrease with temperature. When you move from 25 to 30, then definitely this water line will shift like this. Yes or no? This water line will actually shift like this because the dynamic viscosity of liquids will actually decrease with temperature. Okay, so when dynamic viscosity of liquids is decreasing with temperature, the slope, because obviously we know mu is equal to tau divided by du by dy, and since these are Newtonian fluids, Newton's law, and both these are Newtonian fluids actually here. So in case of Newtonian fluids, this lines pass through origin. So at any point, slope is nothing but the ratio of tau by du by dy. Now when temperature increases, definitely this line will actually shift down because this slope is equal to tan theta, you know, correct? So slope is equal to tan theta. So obviously, and slope is actually tau by du by dy actually here. Okay, so this is slope. So as temperature increases, obviously this quantity will decrease. That means this theta should decrease for liquids. So obviously in this case, this water line will actually slightly decrease its slope. But in case of air, as you know, air is a gas. In case of gases, dynamic viscosity will increase with temperature. So at 30 degrees Celsius, if you see, this line will actually slightly increase its slope, and these two lines will actually move close to each other, because in case of liquids, dynamic viscosity will decrease. In case of gases, dynamic viscosity will increase, and this effective angle theta dash, let us say, so this theta dash will be less than theta. So as temperature increases, theta decreases. Okay, so for answering this question, you should know two concepts: that when temperature increases, dynamic viscosity of liquids decrease because of the reason I have given you equation, and in case of increase of temperature, dynamic viscosity of gases will increase again. Yeah, but for gas, theta will increase. Okay, theta is the angle between these two lines. Okay, not with x-axis. Clear? Okay, maybe here you got confused. This is alpha, let us say, for example. Okay. Yeah, for gases, dynamic viscosity will increase with temperature. Clear? Okay, so is this clear to all of you? But this is a one very wonderful question which generally comes out in interviews. The theta dash will actually decrease. So in which temperature both slopes will be same? That depends upon the constants in the laws that I given you. Okay, like power n. In the liquids case, a plus ln a into e power minus bt, all these things. So that depends upon the constants. Clear? So anyway, this is the story of, on an average, kinematic viscosity and dynamic viscosity. Now let us see certain applications on kinematic and dynamic viscosities, obviously. Okay, so let us see, if you have a plate, for example, let us suppose if this is moving at velocity u, for example. Okay, so let us suppose if this is moving with velocity u. Okay, now in order to maintain this flow, let us suppose if this is mu, of course, if the fluid is having a dynamic viscosity of mu, then what is the force F you need to move this plate, obviously. Okay, so that's what you have. Let us suppose if A is the area of the plate. Sorry, in which temperature both, yeah, I have explained you. Okay, now let us suppose if you want to calculate what is the force F, you know, F is equal to mu into, F is equal to shear stress into area, obviously. Okay, so F is equal to shear stress into area, and shear stress is equal to mu into du by dy into area. Now let us suppose if I give you this function, that velocity is only a function of this. Okay, v is equal to, or u is equal to, let us suppose if this is moving with u infinity, u infinity y by, let us suppose if this gap is h by h. Okay, so let us suppose if this is the function, then if you differentiate it with respect to y, this gives you du by dy is equal to u infinity by h. There is no dependence on y, so mu into u infinity by h into area is what you have here. Okay, so that's what you have. Clear? And then let us see certain other examples. Like for example, I'll teach you one different example which that you can answer things. Let us suppose there is a shaft. Okay, so there is a shaft like this. Okay, there is a shaft like this. Now this shaft has a diameter d and length L, for example. Okay, so let us suppose length is L. Now you all might have seen this case of this, correct? So let us suppose if there is some viscous oil in this, then to pull this shaft F, what is the force you required? Correct? You all have done this? Yes or no? How many of you have done this? Example, generally if there is a shaft and if there is a sleeve in which the shaft has to be pulled at some velocity V, then what should be the force F applied? Do you all know how to solve this? Yes? Yes or no? Yes. Correct? So this time, for a slight change, what we are doing is, let us keep inclined. Okay. So this is a linearly clearance shaft. Okay, understood? So basically the clearance between the shaft and the sleeve is actually linear. It's not a straight clearance. Okay, then I'll explain you for a constant clearance also. If you have the answer for straight clearance, you can do for constant clearance. Okay, now let us see what you can do actually. This is H1 and this is H2 obviously. Okay, so this is H2. Now if this is H1 and if this is H2, then let us see. Can you tell me one thing? Let us suppose if this shaft is actually moving with a velocity V. At all these locations you have the fluid. At every section. Now try to answer these two questions. You will be able to understand this. Let us suppose if I take these two sections, for example, this is first section and this is second section. Clearly at these 2 points the velocity is 0. Yes or no? Because the sleeve will not move, so sleeve will be fixed. So if this is fixed, then definitely velocity at this point and also at this point will be same. Correct? Yes or no? Come on guys, please type in the chat box. Yes, if these two are fixed, then these two are fixed points. So they have same velocity, which is V is equal to 0. But here also the velocity is same, because if this shaft is moving with velocity V, then definitely these 2 points also have the same velocity V. That means these 2 points have 0 velocity, fine. These 2 points have V velocity. So that means if you write the velocity gradient du by dy, for example, this du is same at these 2 sections. But is this dy means the gap in which this velocity is increasing, is it same here? The gap with which the velocity is increasing from 0 to V, is the gap same at these 2 locations, at these 2 sections? No, it is not same, correct? So if that is not same, then definitely this velocity gradient is not same at the both sections, and since this depends on tau, this tau is also not same at both the sections. Clear? Now therefore, if you want to analyze this situation, if you want to calculate what is the force acting, let us do one thing. Let us take some small section of the shaft. Okay, so let us take some small section of the shaft actually here. So let us suppose here there is a sleeve like this at this location. So there is oil. Let us suppose if this height is hx, for example. Okay, so this is hx. Now if this is hx, clearly you can see within a small gap you can assume a linear velocity profile. So let us suppose at this point velocity is changing from 0 to V. Okay, so 0 to V. Can I say at that small section elemental shear or shear stress acting at that section is equal to mu into du by dy, which I can write as mu into, let us suppose at this section if I take that, if this height is hx, can I say mu into V divided by hx? Can I say this? Yes or no? Because within a gap of hx, this profile is changing by a velocity V, of course. So can I say that mu into V divided by hx? Can I say it? Everyone, please type in the chat box. At some particular location, x, let us suppose if this is your coordinate system, this is the x-axis. So this is x is equal to 0. Obviously, this is x is equal to L, because this is a shaft of length L actually. Okay. So if this is a shaft of length L, here if it's x is equal to 0 and here if it's x is equal to L, then can I write this V by hx? Okay. Now, because of this small elemental force acting is tau into dA, which is mu v by hx into dA. Can anyone tell me what is dA? Let us suppose if I take this small thickness as dx, can anyone tell me what is the area of fluid solid contact if this length is dx? If this length is dx over that strip of circle, can anyone tell me? Like first derivative principle, we'll see. Okay, so can anyone tell me if this is dx, then can anyone tell me what is the area of fluid solid contact, means the fluid and shaft contact actually at this case? This is a circular shaft. Okay, this is a circular shaft. So at a distance x, can you feel what's happening? What could be the surface area? Like for example, this is nothing but so undoubtedly this is the area which comes in contact with the fluid actually. So can anyone tell me what is this area? This is a diameter d, this is dx, so what is the area that's in contact with the fluid of that small elemental circular strip that I have taken? Pi d into dx, correct? Obviously this dA is actually pi d into dx, correct? Pi d into dx. As I know, because pi d is the circumference multiplied with dx is the area that's coming in contact with the fluid. Now obviously this is the expression for small force, means a small amount of viscous force acting on this thing. So if you want the total, you have to integrate this. So therefore F is equal to integral x is equal to 0 to x is equal to L mu v pi d by hx into dx actually here. Okay, so this is dx. Now you can understand one thing, that how to write this hx. Hx will be, means height at any section will be h1 minus into x. So this is what you have. It's very easily understood. Look, let us suppose if this is x axis, you have a line like this. For example, let us suppose if this is y axis and this height is h1, this height is h2, this length is L, and let us suppose at some distance x you take this height as hx, for example. Now if I plot these coordinates, this coordinate is nothing but 0 comma h1, this coordinate is nothing but x comma hx, and this coordinate is nothing but L comma h2, correct? Yes or no? If I mark these points as A, B and C, then all these 3 points are on a straight line, because this is a tapered sleeve, so it's a straight sleeve actually. If this is the case, slope of AB should be same as slope of AC, correct? If I do this, what I can get, slope of AB is nothing but h1 minus hx divided by x is equal to, because this is the y difference, by h1 minus h2 by L obviously. Okay, so if you simplify this, hx is equal to h1 minus h2 by L into x. This question you also have done in strength of materials. You might have seen there is a tapered shaft from diameter d1 to d2. There is an axial load applied. What is the elongation in the tapered bar? You might have done this question. Okay, so there is the same situation like this. You have a shaft from diameter d1 to d2, and if you apply a load P, then definitely we will see delta is equal to 4PL. If this is length L, then pi E d1 d2. You might have seen this, something like this. Yes or no? So then how do you calculate the intermediate diameter? Same, using this condition. Okay, so if you do this integration, means if you, this is a function of x, if you put it here and if you do the integration, you will directly get something like pi mu v dl by h1 minus h2 into ln h1 by h2. Okay, you can try this integration actually in the later. This, the only thing is, this hx is actually in terms of x, actually it's a function. So if you put, it's a single variable integration, you know, you have done your integration techniques. So if you do this integration, this is what you will get. Clear? This is the force which is required to pull the shaft in that particular clearance. Okay, clear to all of you? Did you all understand what to do? So these are somewhat similar to journal bearing. Yes, this is a journal bearing. The only thing is the clearance is actually tapered. That's it. If clearance is tapered, shear stress at every location on the shaft changes. Okay, so if shear stress at every point on the shaft is changing, then how we calculate is what. Now I would like to ask you one question. Now many of you will answer, I know this. Let us suppose if you have a shaft, if there is a constant clearance, if this constant clearance is a C and fluid is same F and this is moving with a velocity V. Okay, now if this is F and V, so PDF काम मिलेगा, in the description you have the links and all, you can go there directly. Okay, in the app it directs you to a particular page. Now in this case you might have seen F is equal to, if this is of length L, which many of you might have seen, pi mu VDL by C is what you might have written. Yes or no? Is this the expression that you have written actually? Type in the chat box, is this the same expression that which you have written for this case? You might have known this, right? Pi mu VDL by C, obviously. Correct? You might have seen this. Yes or no? Have you done this? So please type in the chat box. Have you done this actually? Yes, you all might have known this formula. Okay. Now this is the most general case of this actually. Okay. Now if H1 is equal to H2, definitely you can understand one thing. If H1 is equal to H2, what you have actually here is, this is what you have, H1 minus H2 by ln H1 by H2. If H1 is equal to H2, if this H1 is equal to this H2, this case will get converted to this case. Yes or no? Okay. So if H1 is equal to H2, then that means both are same. So if H1 is equal to H2, this tapered becomes straight, and clearly this is the question what you have. Okay. So for which you know the answer, which is pi mu VDL by C. If you do this little analysis, you will get the same answer. Okay. So if you see, for example, F is equal to pi mu VDL by H1 minus H2 ln H1 by H2. Okay. Now try to understand one thing. If I take H1 common, you have 1 minus H2 by H1 into ln H1 by H2. Now clearly you can understand one thing. If you put H1 equal to H2, this becomes 0 and also this becomes 0. So it's 0 by 0 form, correct? So in maths, you know, limits, if you apply, if you are getting 0 by 0, what you will do generally in limits? Let us suppose if H1 is coming very close to H2 and if H1 and H2 are almost equal, then in that case, this gives you 0 by 0 form. So what do you do in case of 0 by 0? What do you do in case of 0 by 0 in maths? Come on, quick. L hospital, right? If you see, let x is equal to H1 by H2, for example, then this or H2 by H1, this could be little simple to do, H2 by H1. If you look at this term, because the main issue is with this term only, okay? So this can be written as, if H1 is tending to H2, limit x tends to 1. This is H1 by H2. So if you want to write it as H2 by H1, ln H2 by H1 whole power minus 1. So log power minus 1 can, that minus 1 can come forward. So minus ln x by 1 minus x. This is what you have. Yes or no? Correct? So this is what you have actually. So if you take this, then if you apply this L hospital rule, you can clearly see limit x tends to 1 minus 1 by x into derivative of denominator is minus 1. So this gets cancelled and limit x tends to 1 by x is 1. So when H1 is tending to H2, this ratio becomes 1 and you have pi mu VDL by C, which is actually this. Got it? Okay. This I have written because this can be written as minus ln H2 by H1. So that's why I have written as minus ln x by 1 minus x. Clear? So if this is giving you 0 by 0, if you apply L hospital, this gets converted to 1. So that's how when H1 is becoming H2, this ratio will actually tend to 1 and this expression is same as this expression, whatever you have here. Okay. So for the rest of the things, I'm going to give you formulas directly. Okay. So see, if you want to rotate this shaft in a sleeve, for example, if you want to rotate this in a sleeve actually, okay. Now you can see if there is some viscous oil which is present here, of dynamic viscosity mu. This is a dia d and this is a length L. Now let us suppose instead of pulling, you want to rotate this shaft at some angular velocity omega. Okay, so let us suppose if you want to rotate this at some angular velocity omega. If you want to rotate this at angular velocity omega, then clearly you know torque is equal to force into radius. Okay, so let us say dt is equal to df into r, for example. Now clearly if you take any section, you can see these are the points of solid fluid contact, and at any location this solid fluid contact points are clearly at a radius r from this axis of rotation. Correct? The radius of fluid solid contact points from this axis of rotation is capital R at any location. So this is fixed R. What is df? The shear force acting, just now we have seen shear stress into pi d dx into R. Okay, this is what we have, and shear stress is equal to mu into velocity gradient. So if this clearance is c, for example, within a small clearance c, like for example if you exaggerate this, clearly you can understand at every point the velocity will be r omega. Yes or no? R omega means here the velocity is 0 because of no slip. So within this small clearance c, velocity is increasing from 0 to r omega. That means velocity gradient is written as r omega by c. Right? This is what we can write. Yes or no? Velocity gradient is actually r omega by c multiplied with pi d dx into r. So if you integrate, this is d torque. So if you integrate this from x equal to 0 to x equal to L for length of shaft t, L t is equal to pi mu omega r d by c, r square d by c into L, obviously. Correct? So if you simplify this, we have pi mu omega r cube L or d cube L, for example if you write d cube L by 4c is what you have here. Correct? So this is the expression for the torque. Yes or no? Pi mu omega d cube L by 4c. Yes. So similarly, what is the power? Power is equal to torque times omega, which is equal to pi mu omega square d cube L by 4c is what you have. Okay, because this torque multiplied with omega gives you power actually in this case. Got it? Yes or no? Similarly, if you have a disk, for example, you can see in the case of a disk, if you have the case of a, if you have the case of a disk actually here, so let us see if you have some fixed base like this. If you have a small clearance C, okay, and let us suppose you have an axis about which this disk is actually rotating. Okay, so let us suppose this disk is getting a small handle here, for example. Okay, so like this, you have the small handle. Okay, and this is a small handle, and let us suppose you are evolving this disk at an angular velocity omega. Okay, and you have this thing here. So practically what you should do is try to understand, whenever you take two sections, again at this location and also at this location, at these two locations this velocity is 0, correct? At these two locations C is same, but whenever this disk is evolving at this point and at this point, is the velocity same? Means the velocities of points on the disk at different radius, are they same? Are they same? Are the velocities on the disk at these two different points, are they same? Let us suppose if the disk is evolving. Okay, it's rotating, sorry. If disk is rotating, then definitely velocities at those 2 points are not same, because obviously this point is at a radius r1 and this point is at a radius r2. So r1 omega and r2 omega are not same, obviously. Okay, so that means even in this case shear stress actually changes from point to point, obviously. Okay, so shear stress will change from point to point along the axis or along this radius. Okay, so along the radius you can see shear stress actually changes. So clearly at some location r, for example, if you want to see, we have d torque is equal to df into r, and df can be written as tau into dA into r, obviously. So tau can be written as mu into r omega at that point into this dA. Now the dA in this case is, let us suppose if the disk is rotating on that particular flat plate or having this viscous oil. If you see the top view, that means, can I say in the top view how you see is basically this is the disk, this is the center. So all the particles at a radius r with a small variation dr, if this is radius r actually, then all these particles at a radius r will have same shear stress. Yes or no? Can I say this? So that means this dA is actually 2 pi r dr into r, obviously. Okay, so if you integrate, this is expression for dt. So if you integrate this, T is equal to pi mu omega d power 4 by 32 times clearance. Okay, so this is what you have actually here. Okay, so we have that particular expression. Similarly, in a cone, if you have the conical block, if you have a conical block and if you are rotating, for example, let us suppose if this angle, half of the angle is theta, okay, half cone angle is theta, and if here there is a fluid, if the clearance is actually c, then tau is, or torque is equal to pi mu omega d power 4 by 32 c sine theta actually here. Okay, so this is the torque, which is pi mu omega d power 4 by 32 sine theta. Very simple again. So you take a small element at any particular location, the clearance is c, so this radius is r. So if you integrate this over 0 to capital R using d, this is what you have. Okay, so T is equal to pi mu omega d power 4 by 32 c sine theta. Clear? All these are very simple derivations, nothing big to worry actually. Okay, very simple derivations, but because of little time constraint, I'm not doing today. Okay, so this is what we have. Now based on this, we would like to solve 1-2 questions actually. Okay, because let us come on solve this. I'll connect a pole for this. Okay, so you can do. Cylinder of 0.12 meters radius rotates concentrically inside a fixed hollow cylinder of 0.13 meters radius. Both cylinders are 0.3 meters long. If torque of 0.88 Newton meter is required to maintain an angular velocity of 2 pi radians per second, the dynamic viscosity of the liquid which fills the space between cylinders is approximately. I'm giving you 2 minutes, so please solve. Okay, so I'm giving you options, so please solve this. These all are standard results, yes, basically. Okay, so solve this. Just a minute, so please solve this question. Basically, there are 2 cylinders in which you have certain annulus. Come on, type it in the chat box. I mean in the pool. So there are 2 cylinders. Okay, so I'll also be solving with you, so please use the poll meanwhile. Let us suppose if there are 2 shafts, I mean if there are 2 shafts actually like this. Okay, and both these are of equal length. Okay, so so you can clearly see. Okay, now both these are of same length L. If both these are of same length L, okay, sorry, fine. So if this is clearance C actually, now you know obviously the torque which you require to rotate, just now you have seen T is equal to pi mu omega d cube L by C, I think 4, right? Yeah, 4C, correct? That's what we have got when we have analyzed. Yeah, 4C. Okay, now if this is 4C, now let us see what they're giving. Torque of 0.88 Newton meter is required. So 88 by 100 is equal to pi mu is not given, angular velocity 2 pi into d cube. So what is the diameter of the shaft actually? Of the inner shaft, because this is the one which is rotating. So the cylinder of 1.2 meters radius rotates concentrically inside. So this is of 0.12 meters radius. So diameter is 0.24 obviously into length. So what is length actually? Length is 0.3 meters long divided by 4 times clearance. So what is the clearance? This shaft is of radius 0.13 meters. This inner shaft is of radius 0.12 meters. So this clearance is obviously 0.01 meters obviously. Okay, so the clearance is 0.01. So this is 10 power minus 2 obviously. So you have only one unknown. So you have to calculate this mu. Come on, do this. Mu, if you calculate, you will get in Pascal second. Okay, so please do this. Come on, solve this question. So yeah, we can what we can do, maybe we can use the calculator directly. So 0.88 into 8 into 0.88 into 4 into 10 power minus 2, 0.04. So this is the value divided by then 2 pi square into 0.3. So 2 into 0.6 pi square, 0.6 pi square actually. Okay, so 0.6 pi square, this divided by 0.24 whole cube. Okay, so divided by 0.24 whole cube actually. Okay, so this gives you 0.4299, 0.4299 pascals second, correct? Oh sorry, 0.397 is coming. Let us check the calculation once again. Yeah, 88 by 100 is equal to pi into mu into 2 pi square into 0.24 whole cube into length of the shaft is 0.3 of course. So diameter is 0.24 obviously by this is 0.01. Yes, everything is correct. So 4 into 0.01, right? So let us check this calculation. 0.88 Newton meters, 0.88 into 0.04. Just a minute. Yeah, 0.88 into 0.04. This value divided by 0.6 into pi square, 0.6 into pi square, 0.6 into pi into 0.24 whole cube, 0.24 whole cube. Okay, so this value is coming out to 0.429, right? We have written the terms correctly. Pi mu omega is 2 pi radians per second. Okay, d cube. So d cube is 0.24 because this cylinder is of radius 0.12. So this is obviously 0.24 is the diameter obviously, correct? So you are getting 0.397. Okay, fine. 0.397 Pascal second. Okay, so C could be the correct answer then. Please check the calculations once again. Okay, so C should be the correct answer, I guess. Yeah, because majority of you are getting that 0.397. I think some calculation I'm missing out somewhere here. So d cube L by 4C. But anyway, yeah, 0.397 is as many of you are telling. That's the correct answer, I guess. Because we want mu from this. Okay, so this is the one equation, one unknown you can solve easily. Okay, so C. Let us see how many of you have marked C. Oh, why? Poll is not working on YouTube. Because this is actually a poll especially for YouTube actually. Okay. Fine. Okay, so let us see one more question. Okay, this I haven't taught, I'll teach you tomorrow. Maybe the types of fluids. Yeah, you can see this. A shaft of diameter d and length L is rotating at n rpm in a journal bearing. The clearance between the shaft and the bearing is y, and the filled with an oil of dynamic viscosity mu. The expression for the power absorbed in overcoming the viscous resistance is calculated as mu L n square by 3600 y into pi d power m actually. Okay, okay, poll is not working. Fine. Yeah, it's okay. We'll go without this poll. Fine. Okay, so see here. Please solve this question. What is the value of m? So m is actually given some power on the top of this pi d. Now let us see what they're telling you. A shaft of diameter d. So this is a shaft of diameter d actually, and here we got a length L obviously. Okay, now this is inside a sleeve, inside a journal bearing obviously. So this is inside a journal bearing, and this clearance is actually C. Okay, so if this clearance is C, so diameter d and length L, this is rotating at n rpm, actually, rotations per minute obviously. Okay, so inside a journal bearing, clearance between the shaft is y, so this is actually y. The expression for the power absorbed. So first of all, we know power is equal to torque times omega. So torque, we have just calculated pi mu omega d cube L by 4c. Is this expression correct clearly? Yes or no? Because you can see 0.49 only coming, right? Yeah. So in this question, I think 0.49 is the correct answer, because even we are getting that. So this expression is correct, right? We have calculated this. So T, the power that you require, T is equal to pi mu, so tau into pi d dx into R, obviously pi d dx correct into R, mu into R omega by c is the shear stress, mu into velocity gradient, R omega by c into pi d into dx into R. So if you integrate, this mu comes out as constant, omega comes out as constant, pi comes out as constant, this d comes out as constant, this R square comes out as constant, L comes out as so obviously this c also comes out. Integral 0 to L dx is L. So pi mu omega d cube L by this R square can be written as d square by 4. So 4c. Yes, this is correct. So then definitely we can use this. Okay. So pi mu omega d cube L by 4c into omega, obviously. So this is the power. So P is equal to pi mu omega. Omega can be written as 2 pi n by 60, or this can also be written as pi by 30 times n. Okay, because it's angular velocity, d cube L into omega, again pi n by 30 into 1 by 4c. So this is 4y actually. Okay, so this is the expression. So P is equal to, from this case, P is equal to, so first of all, if you see mu, there is only one dynamic viscosity, there is only one L. So mu we have taken, L we have taken, then n is here and also here. So n square divided by, now if you check this constants, 30 into 30, 900, 900 into 4, 3600. This y is also here, so you take y here, into, now pi is 1, 2, 3 times, d cube is also 3 times, so pi d whole cube is what you have. Okay, so this is what you have here. So pi d whole cube, so d is actually, this m value is 3, because this is m, so that m and this 3 are same actually. Okay, so d is equal to 3. Clear? So is this clear to all of you? Please type in the chat box. Is this clear to each and every one of you? Okay. So m value is actually 3 in this case. Okay. Fine. So please provide the PDF. Yeah, definitely you'll get the PDF. Okay, don't worry. Then you can see one more question, maybe. Yeah, this question you can see directly. A shaft with a diameter d is equal to 80 mm and length L is equal to 200 mm shown in figure. Okay, I think figure was missing actually. So it's okay, no need of figure. We have this shaft. This is of diameter d, or diameter d is equal to some 80 mm and length is given something. Okay, now is pulled with a constant velocity u. So let us suppose if this is pulled with a constant velocity u to a bearing of variable diameter, the clearance varies from 1.6 to 0.4. Okay, so clearance varies from 1.6 mm to 0.4 mm. Similarly, it's a shaft actually. Okay, so it's a circular shaft obviously. Now is filled with a Newtonian lubricant whose dynamic viscosity is 0.1, 1 poise basically. Okay, so this is 1 poise obviously. Okay, so this is 1 poise. The axial force required to maintain the movement of the shaft. So what should be the force F that you need actually? Okay, so you have seen just now, F is equal to pi mu VdL by H1 minus H2 ln H1 by H2 actually. Okay, now you can see pi mu. So what about mu actually? 0.1. V, it is pulled with a velocity of 4 meters per second. Diameter 80 and length 200. Okay, so 80 into 200 into 10 power minus 6 obviously if you convert to meters by mm. 1.6 minus 0.4, so 1.2 into 10 power minus 3 because it's in mm into ln 1.6 by 0.4, so this is ln 4. Okay, so if you simplify this, 10 power minus 6, these couple of zeros and this, okay, this two if you get cancelled, this is 10 power minus 4, then this is 10 power minus 1, then this is 12, this is 3, so 16 by 3 ln 4. Okay, so 16 by 3 ln 4 is the actual value. So let us check this, ln 4 into 16 by 3. Okay, so 7.393 newtons. Okay, clear? I have just told you this, how this is coming because of this logic. Okay, so you can see here this simple integration will actually give you this formula which can be used directly here. Okay, 7.39, yes, 7.39 is the correct answer. Okay, 7.39 is the correct answer actually. So if velocity profile is parabolic, then same formula used. Actually, if velocity profile is parabolic, when you are calculating du by dy, you will get a linear function. Okay, so you have to put a particular value of y. Like for example, if I give you u is equal to 2y minus 3y square, for example, okay, then if I ask you shear stress at y is equal to 0, for example, at the wall, then mu into du by dy at y is equal to 0, mu into, if you differentiate this, 2 minus 6y at y is equal to 0. So if you put y is equal to 0, you will have 2 mu. That's how you will actually do. Okay, if you have parabolic profiles or any profile, they'll give you the value of y at which you have to calculate the shear stress. Clear? Got it? Now I'll ask you for one question, so please solve this. I'll give you some time. I'll also give you one expression that moment of inertia of cone is equal to 3 by 10 mr square. Means if this is r naught, base radius is r naught square. So this is r naught actually. Okay, so this is moment of inertia of the cone about this axis. So please tell me what happens here. There is a viscous oil in this channel. Okay, there is a small clearance, they have viscous oil. So normally we all know that expression for the torque acting on the cone is actually equal to pi mu omega r naught power 4 by 2 times of c. Okay, so 2 times of h here, for example. This is actually the formula, or pi mu omega d naught power 4 by 32 times of h. Anything is same because r naught can be written as d naught by 2 actually. So anything is same. You know this, and you also know T is equal to I alpha, but of course this is with a minus because this torque, viscous torque, is actually stopping this rotation. Okay, so that's why there is a minus. So solve this question. This you know, correct? And this also you know from mechanics. So please solve and tell me which is the correct option in this case. This is a solid cone. Basically it has a cone angle of 2 theta, so that's rotating initially at an angular velocity of omega naught. Okay, but obviously the physics that happens here is because of this viscous effects, the speed of this cone will decrease. Yes or no? Let us suppose initially if it is rotating at omega naught, now if you stop applying any external force for rotation, then because of the viscous effects around the cone, the velocity of the cone, the angular velocity of the cone will actually decrease with time, correct? So what is the expression? That's what we have. I'm just giving you this hint. I of cone is equal to 3 by 10 m r naught square. Okay, so please solve this and tell me the options, which are the correct options here. Sin theta will not come. Sorry, it will come. Yeah, this is sin theta. In case of cone, it is sin theta. Did I mention here when I'm writing this previously? Yeah, this should be a sin theta, correct. A is the correct answer. 5 mu r naught square t by 3 pi h 5 pi and all. Okay, so let us check. See here, we all know T is equal to minus I alpha because this minus is because this torque is actually viscous torque. Okay, so pi mu omega r naught power 4 by 2 h sin theta is equal to minus 3 by 10 m r naught square into d omega by dt obviously. Okay, then you can see, simplify this. This 2 cancel this 5 times, this r naught square cancel this 4 2 times actually here. So this implies pi mu r naught square or 5 by 3 m h sin theta into this omega into dt is equal to this omega. If it comes here, this is 1 by omega d omega actually here. Okay, with a minus sign obviously because this minus is also there. Now if you integrate this, clearly you know this is a time integral. So at time t equal to 0, omega is actually equal to omega naught. It is rotating with some initial angular velocity. At time t, if this is omega, then clearly you can see minus 5 pi mu r naught square by 3 m h sin theta is equal to ln omega by omega naught. So omega is obviously equal to omega naught into exponential of minus 5 pi mu r0 square by 3 mh sine theta. That's it. Okay, so this is the expression for the angular velocity of the cone with the time t. Okay, clear? So you can see obviously in this, like here pi is not there and these are not cubes, so these are wrong. A is the correct answer. Okay, clear? Option A is the correct answer. Yes. Is this clear to all of you? You all know engineering mechanics, and also this basically calculating this torque is the fluid mechanics part in this. Okay, so if you know how to calculate this, then definitely you can write an expression for this. Okay, and you know easily calculating this. Let us suppose even in exam, if you don't know this, you can easily calculate this, because you can see, let us suppose you have a x and y axis. How do you get a cone generally? If this is xy, okay, and if this is the line y is equal to mx, then definitely by rotating this line about the x-axis, you will form a cone, correct? Like the volume of solids and all, you can get. Let us suppose if you rotate this line about this cone, about this x-axis, you will form a cone actually. Okay, so let us suppose if the cone height is h, and if the base radius of the cone is r, if this is theta, and this coordinate is h comma r, obviously you know tan theta is equal to m is equal to r divided by h, obviously. Okay, now if you take a small portion here, when you rotate, this is y, for example, this if you take for thickness dx, then elemental moment of inertia is equal to, you know, basically for small mass, let us suppose if the volume, if the thickness is dx, we have rho into pi y square into dx, so this is the mass of the cone, into r square, which is y square by 2, obviously. Okay, so you can integrate this from x is equal to 0 to x is equal to h, x is equal to h, yes. So rho pi dx or pi by 2 into y power 4 can be written as m power 4 x power 4 dx. So if you integrate this, obviously you will get 3 by 10 m r square is what you will finally end up, because this m is actually equal to density into 1/3 pi r square h. Okay, this is what you can do, and this m is nothing but r by h actually. So if you do this integration, you will get this easily. Fine. Okay, so this is how you calculate the moment of inertia of the cone in general. Very simple. Okay, this is basically a small disk. So for disk, m r square by 2, and if you use that m r square by 2 and if you integrate, you will get this 3 by 10 m r square. Clear to all of you? So this is how we can get this expression. Basically, this calculation of the torque is the fluid mechanics part in this, and this is the engineering normal static dynamics part. Okay, perfect meaning of fluid mechanics. Now we are applying principles of mechanics using terms in fluids. That's it. That's what we call fluid mechanics. It's very simple. Okay, so I'll give you some small homework for you based on what I have taught you today. Okay, so you can see that this question and this question I'm leaving you for this. Okay, so basically there are two liquid surfaces which are having things like this, and then they are asking you the viscosity ratio of mu2 by mu1. So here if it's mu2 and here if it's mu1, then what is the ratio of mu2 by mu1, and also force exerted by liquid 1 on upper plate, force exerted by liquid 2 on lower plate. Means basically what is this force exerted on the upper plate and what is the force exerted on the lower plate by mu2. Okay, so this is one question. You please try. I have given the velocity profiles in both the sections. The coordinate system I have taken here. So this is 0, x, and this is y, obviously. Okay, and clearly you can see this is second question. Basically there is a cylinder which is falling in a vertical channel of thickness h, and this length of the cylinder is L. Then what is the velocity? Don't get worried of this expression by looking at this expression. This question is very simple actually. You have to solve a single differential equation. That's it. Okay, so obviously this is an again easy question. Basically this block, if you release this block with respect to time, what happens is its velocity will take this function. You will see this very nicely. Okay, if this is velocity, initially the block velocity, it starts from 0, velocity will increase and it becomes stabilized after some time. Okay, so what is this V terminal? That's what you have to calculate. Okay, so that you can apply simple mass balance, simple force balance equation. Weight minus viscous force is equal to mass into acceleration is what you have to use. Obviously if you use, you can frame a single differential equation, single variable, and it's a variable separable form. Okay, so you can directly go for integration. Clear to all of you? So please solve these two questions. These two questions, take it as your homework. Okay, and we will basically, I thought of finishing. Did I make justification for this train? You see, it's coming very fast with fire. Yes or no? Yeah, Telegram, correct. You know, this Telegram is also there. You can actually join in this. Okay, fine. If some of you feel it's helpful, you can join over here. Okay. Okay, so I hope I have justified this diagram. Many of you were worrying about this speed. Okay, but anyhow, I'll try to reduce the speed, but again, it's fast track, so you know, we have to cover certain things in a very stipulated time. Okay, so tomorrow we'll look at some other properties and also hydrostatics. Okay, so pressure variation in a static fluid in different mediums. Okay, we will see in liquids, in you know, atmosphere, which kind of variations are there. We'll see manometers, piezometers, some drawbacks of piezo, some drawbacks of manometer. All these things we'll see in tomorrow's session. Okay, clear? So did you all learn some nice concepts in this session? Because it's a quick revision, so I was not able to go to much depths at many locations, but I hope this session is helpful to all of you. So कब तक चलेगा FM? I think November 18, but of course you have some holidays, Diwali holidays in between. Okay, so thank you all. We'll meet again tomorrow at 7:30 AM and we'll continue our discussion on types of fluids. Basically non-Newtonian also I'll discuss a bit, and then we'll start about hydrostatics. Okay, pressure and its measurements. Okay, so thank you all. We'll meet tomorrow. Okay, any doubts? Any quick questions? Well explained session. Thank you. Yeah. Okay, so fine. Thank you all. Then signing off. We'll meet tomorrow at 7:30. Thank you.